Hello, peoples. This video is intended to help you with equilibrium problems. Now, equilibrium means that the forces add up to zero, everything's in balance, however you want to say it. But if the forces add up to zero, that means the acceleration is also zero, which means the object is either stationary or moving at a constant speed. This will be reviewed in our wrap-up at the end of the video. But it is still a dynamics problem, and dynamics problems have the same general problem-solving strategy. By now you should know, FBD, forces X, forces Y, but because it's an equilibrium problem, the acceleration is zero in both cases, which makes life super easy. This scenario here has a mass hanging from two strings, and we're trying to figure out the force exerted by these two strings. So, as I was saying, let's get started with, not that. This video will not be edited, and why I jumped down there, I got no idea. I was gonna say, let's start with a free body diagram. That was what I was gonna say. So let's do that. I'm gonna draw a free body diagram. We've got the force of gravity acting on the mass, Fg equals mg. We have two ropes here. So one of the ropes is at 37 degrees. I'm just gonna call this FT, I'm going to go with 2 on the right side. I don't know why. And then FT1 on the left side. Technically, this would be theta 1, and this would be theta 2 associated with each rope. Yes, I know we know the values, 55 and 37 degrees. I'm just doing a generic setup here. So there's my free body diagram. You know the next steps, ladies and gents. We have a little sum of the forces that cause the mass to not accelerate in this case. This is 0. Just looking at my free body diagram, I have the tension to the right at an angle of theta 2. I have a tension to the left at an angle of theta 1. And that adds up to nothing because the forces add up to 0. In the y-axis, well, it's not accelerating. Terrific. So look at the free body diagram. We have Ft1 sine theta 1 and Ft2 sine theta 2. And we have the force of gravity acting down. They add up to 0. Yes, I'm doing this algebraically on purpose because I would like you to just see one thing in particular. I'm just going to move the negative to the other side. I don't like negatives. I'm a positive kind of guy. So there we go. And that's about it. I mean, if you wanted, you could move the gravitational force to the other side. I know I said I don't like negatives, but I'm just saying. All right. In the end, though, what I do want you to be aware of is for most of these problems, I mean, some of them could be very straightforward and easy to solve, but you know me. I'm not going to make it that super easy. What I do know is that there can be multiple unknowns. So in some cases, you won't know either tension. Okay, and that's this problem in particular. So in this equation, I have two unknowns, and in the expression for the y, I have two unknowns. Hey, I've got two equations with two unknowns. Your choices are to isolate and set equal, or isolate and substitute. I mean, that's totally up to you. Okay. Another option would be is if we don't know anything about this whole side here. Okay, we don't know Ft2, and we don't even know the angle. Over here, I don't know Ft2, and I don't know the angle. What a surprise. So in this case, we have two equations, two unknowns. My suggestion here would be to isolate the tension and sub it in. Actually, I would isolate in the x and sub into the y, and you'll get tangent. This problem does not go into that, but my point is, these problems often have two equations, two unknowns. You will have to do a little algebra, a little substitution, isolating and setting equal, however you like to solve the problem. What do you feel most comfortable doing? So anyway, let's get after this, ladies and gentlemen. And I'm going to start subbing some stuff in here. We have Ft2 cosine of 37 degrees, and we have Ft1 cosine of 55 degrees. Clearly, there's nothing I can do here. So, I mean, I can move on to the y. I can tell you right now that we are going to be stuck with unknowns there. So I already know I have two equations, two unknowns. I'm going to isolate ft2 by dividing by cosine 37. And I get that ft2 is equal to 0.718 ft1, excuse me. Again, all I did here was cosine 55 divided by cosine 37. Those are numbers. Cosines and sines are numbers. Don't let them bother you. I'm going to substitute this puppy in here for ft2. Where is it? All the way over there. Okay. So here we go. We have ft1, don't know what it is, sine 55 degrees. ft2 is now 0.718 ft1. This is where people tend to miss things. They're like, oh, I did my substitution. Yeah, don't forget, times sine 37 degrees. Don't forget that. For some reason, like everybody's so hyper-focused on the substitution, you lose the sine or the trig function. Equals, because I'm going to add the mg to the other side, 60 kilograms times 9.8 meters per second squared. Now, don't let this bother you. Some people get a little intimidated by the math here. There's nothing to be intimidated about. Sine 55 is a number. Like, put it in your calculator. Sine 55. I got 0.819 ft1 plus sine 37 is a number multiplied by a decimal number. Just put it in your calculator. 2 times x times 4 is 8x. This shouldn't intimidate you. It's just decimals, so 0.718 times sine 37. That's all I'm putting literally as I do it on the calculator. I got 0.432 ft1 equals 588 newtons. That's the right side of my equation. Now I have two like terms that I can combine, the 0.432 and the 0.819 ft's, and I get 1.25 ft1 is equal to 588 newtons, or 588 divided by 1.25 is approximately 470 newtons. And guess what? Once I get that, I can sub it back in. And I can keep solving. Let me do that. I mean, I'd like to. There we go. So ft2 is equal to 0.718 times the value we got there, which was 470 newtons, times 0.718, sorry, I didn't do this ahead of time, is roughly about 338 newtons. 337, 338, what's the difference? And there you go, peoples. Two expressions, two unknowns, and a little algebra involved. All right, let's summarize this puppy. Equilibrium problems, and basically means that the forces add up to zero. So the acceleration is zero in both the x and the y. And there's two types of equilibrium. There's dynamic, where you are actually still moving, but it's a constant speed. A is still zero. Forces add up to zero. There's static equilibrium, the one we just did, where the object is stationary. And we draw FBDs, do forces x, forces y. And I do want to say that right now we're focused on hanging masses, but in the future, it could be any forces adding up to zero. Like, side note, I could put the electrostatic force, which is, we haven't gotten there yet, but KQQ over R squared. That could be one of our forces. We could do the force of gravity in equilibrium problem. By that, I'm talking about G M1 M2 over R squared. We haven't gotten there yet. But there can be other forces. It doesn't always have to be tensions. Bottom line, the forces add up to zero. And we draw a free body diagram, do the sum of the forces, and have fun. We could also bring a little force of friction into this. Why not? I mean, we can have friction holding something in place. Static equilibrium problem. And again, oftentimes this is two equations, two unknowns, and it requires either isolating variables and setting equal or substitution, whatever your preference is. And this is one particular example. And in class, we did another one where we ended up substituting, I was talking ahead of myself. And we ended up with, if you remember, we ended up with sine over cosine, and we turned that into tangent. And then we ended up doing the angle first. It was the inverse tangent of some number. Okay, that's another option. I didn't do it here because I don't want this video to be longer than it already is. But anyway, speaking of this video, I crushed it. and I'm going to give myself 3 out of 5 stars. I hope it was helpful for you, and I wouldn't change a thing.